All right, I guess we're set.
Okay. Just give me a second here to, well, I got to stop my laptop. Okay, great. So last time, unfortunately, just because of the vagaries of my scheduling, I had to leave at sharp at quarter to the hour, and I was just almost finished. And so I want to try and recap where I was last time. And so we were talking about developing a scaling theory for aggregation kinetics. And it's based on the notion that as a function of time, the mass is growing in a smooth function of time. And so if one rescales your characteristic size by this average size of the clusters, then things should become time independent. And this scaling approach, I showed how it worked in the case of in the case of the diffusion equation, and now I want to show how it works in the case of aggregation kinetics. And as you'll see, it's exactly the same philosophy, and we can extract from this approach very powerful results with relatively little work. And so where we were last time is we started with the equation of motion for aggregation kinetics. So we had an equation for the time rate of change of the concentration. And in the continuous formulation, this is related to an integral on the right-hand side of the product of the concentrations times the reaction rate. And there's a gain term and there's a loss term. And for the sake of brevity here, I'm going to write that integral operator just as I of x. And then what we did is that we made the scaling assumption that the concentration of clusters of mass x at time t is not a function of x and t separately, but it's a very special combination of variables that makes it simpler, in which we write the concentration as some function of x, the size divided by a characteristic size. So this characteristic size depends on time. And so here is also a time dependence, s of t squared. And then the 1 over s of t squared is needed to have a normalized probability distribution. Normalized in the sense that the first moment of this distribution integrated, so the integral dx x c of xt should be something of order 1. And that mandates that we have a factor 1 over s squared in front. And so what we did next, and what I spent a few minutes working on at the end of the lecture, is we take this equation, we substituted into the original rate equation for the concentration, time dependence of the concentration. And so I worked through last time that if you compute the derivative of this, there are two terms that arise, and you get this on the left-hand side. And on the right-hand side, when you substitute this into this integral operator and then rescale everything, one got this function. And so this is exactly where I left off last time. And so now comes the simplification, which is, notice that inside of these curly brackets, there's an integral with respect to v, and the only variable is u. So this, whatever this is, let me define this to be h of u, where h stands for horrible function of u, because it's horrible, but I don't really care about how horrible it is, because all I need to know is that it's a function of u only. And now the next step is, now let's take on the left-hand side of this equation, we have also some function of u. So let's take this and put it on the right-hand side. And so what we're going to get after this step, I'll have s dot over s cubed. And notice here, whoops, one more thing here. We have an s to the lambda minus 3 and an s to the minus 3 over here. So let's just combine this. And what we're going to get then is s dot s to the minus lambda. And so that's basically all the time dependence. And then on the right-hand side, let me move this minus sign over here. So there's the minus sign. And then I have this function, h of u, this horrible function h of u, divided by 2f of u plus u f prime of u. And let me define this thing to be minus capital H of u, which is an even more horrible function of u. But the crucial point here is that on the left-hand side, this is a function of time only, because s is a function of time only. And everything here is a function of u only. And because we have two independent functions of independent variables that are equal at all possible values of the variables, the only way that this can happen is if these things are equal to a constant. And let me define that constant to be capital lambda. And so that is where I should have finished my lecture last time, because that's kind of the punchline here, is that with this scaling approach, we take this very complicated integral differential equation, and with a scaling assumption, we simplify it so that we can separate out the time dependence and the scaled size dependence. And as we're going to see momentarily, well, this is a pretty simple differential equation to solve. This is a much more complicated differential equation to solve, and it's still not solved, actually, but still we can get some useful information by some very simple physical reasoning. So what I want to do next.
We asked you, the sound is no. I think something happened with the connected microphone, the one you have attached.
Yeah.
Yeah, it's working. It's working. All right.
Okay. So how much did I miss?
You were saying that the temporal part is solvable and the horrific, horrible big H is not solved. So.
Right. Yeah. So that's basically where it was. I don't know how I must have hit the button inadvertently. So just remind me if something goes off. Okay. So what we're going to do now is let's look at each of these separated equations and learn what we can from them. Okay, so S dot S to the minus lambda is equal to a constant, which we're calling capital lambda. So this is a very simple differential equation to solve. And so let me not waste time going through the different cases, but let me just write down the solution to this differential equation. And it turns out that there are three possibilities depending on the value of little lambda. And remember, little lambda is the homogeneity index of the reaction rate. So it's telling me how quickly the reaction rate is increasing. Got to figure out how to stand in front of the board. How quickly the interactions are increasing as the size of the clusters are increasing. And so it turns out that there's three possibilities depending on the value of this little lambda. And so for lambda less than 1, and in particular, the case of constant kernel aggregation, which is where I worked through all the details beforehand, that corresponded to lambda equals 0. That was that the reaction rate was independent of the size of any of the clusters. And in that case, it turns out asymptotically, this is t to the power 1 divided by 1 minus lambda. So one has a power law growth in the typical cluster size, and that power law growth starts out as t to the power 1 when we have homogeneity index 0. And as we increase the size of, as we increase the homogeneity index, this power law gets faster and faster. And then something happens when lambda is equal to 1. And for lambda equals 1, then it's just S dot divided by S is equal to capital lambda. And the solution to that is e to the lambda t. So this power law gets faster and faster until you reach the limit of exponential growth of cluster size when the homogeneity index equals 1. And finally, for lambda bigger than 1, one finds 1 divided by t gel minus t to the power 1 divided by lambda minus 1. And here t gel is a characteristic, is the time scale where the typical cluster size blows up in a finite time. So when the homogeneity index is larger than 1, the reaction rate of big clusters is so fast among big clusters that it explodes in a finite amount of time. And so this is the behavior of the time dependence. And in some sense, this tells us a lot about the basic behavior of this aggregating system. So that is the time dependence. And now we've got to go to the size dependence. And here, I'm just going to summarize like maybe 20 years of work on the subject where we now have some general understanding of what's happening. So first point is that because the right-hand side of the master equation was an integral differential equation, it's not been solved. And so what people have done basically is try to look at very special cases or or particular limits. And from this body of work, the following understanding has emerged. So let's look again at Kij. So now I'm going back to the discrete formulation, and you'll see why I'm doing the discrete formulation in just a moment. There's two generic features of this reaction rate that turn out to be important in determining the cluster size distribution. So the first one was the homogeneity index. That is that, so let me put it this way. So Kai Aj is equal to A to the lambda Kij. So there's the homogeneity index lambda. That's one important characteristic. And then there's another one, which is K1, comma J. And it turns out that for many physical situations that we would be interested in, this reaction rate scales as J to the power nu times, hang on a second, let me just make sure I have my, yeah, so this just asymptotically scales as J to the power nu. And what is the meaning of these two exponents here? So let's look at, let me write Kij in a more like, I don't know, abstract form. I mean, this is a huge matrix. It's an infinite dimensional matrix. And so inside of this matrix, there's entries K sub ij. But roughly speaking, we can separate this matrix, this reaction rate matrix, into 4 pieces. So here on the very upper left, that means that both indices are small. So this is the reaction rate of small clusters with other small clusters. Over here in this infinite dimensional, like this infinite part that goes to the lower right, well, that's when the indices are both large. And so this corresponds to interaction rate of large clusters with other large clusters. And then here in these little regions on either side, so this is going to be small, large, and this is going to be large, small. So this is the reaction, this part describes the reaction rate of large clusters among themselves, small clusters among themselves, and these off-diagonal pieces correspond to the reaction rate between large clusters and small clusters. And so what's emerged from, again, many years of studying is that there's 3 generic behaviors. And these 3 generic behaviors are called, not terribly creatively, type 1, type 2, and type 3 reaction kernels. And so type 1 corresponds to when large interactions are much more frequent than all other interactions. So much more frequent than small, large, small, or small, large. And that corresponds to the case lambda is bigger than nu. And so what does it mean here with type 1 reaction kernels? It means that when clusters get large, and now we can think physically about the case of gelation kinetics, where I have molecules that have multifunctional endpoints, and as the clusters get larger, they have more and more endpoints that are reactive. And so the rate at which large clusters are reacting, it gets very quick. And the rate at which small clusters are reacting is small compared to that. And so what happens is that you get huge clusters with a little bit of residue of very small clusters that barely react because the reaction rate is so small. And so in this particular instance, if I look at the cluster size distribution as a function of size, so Ck as a function of k, one generically gets a monotonic cluster size distribution. So something like that. I mean, the actual quantitative behavior is not important here. The crucial point is that it has this feature that there is large clusters react so quickly that they disappear, and all we're left behind is a residue of small clusters. And then there is type 2. And so type 2 is when the opposite limit occurs, where large, small, and small, large interactions among heterogeneous clusters dominates over everything else. So large, large, and small, small. And this corresponds to lambda less than nu. So in this case, what happens is that as the cluster distribution starts to develop, then if there's any small clusters, their reaction rate with large clusters is very large. And so they're swept out of the system very quickly. And in this case, one gets a cluster size distribution or cluster mass distribution, CK as a function of K, that generically will be a single peak. And again, the reason why there's a single peak is that if there's any small clusters left in the system, they'll react very quickly with the large clusters and disappear out of the distribution. And so there's a dearth of very small clusters. And so generically, that's what happens. And finally, the last case is type 3. I'm running out of room here, but I think I can fit it in. Type 3. And so this is the case where large, small is of the order of small, large, is of the order of large, large, which is the order of small, small. Everybody is of the same order of magnitude, and this happens when lambda is equal to nu. And in particular, that corresponds to the simplest case that I worked out all the details for of constant kernel aggregation. And it turns out that, first of all, it's a simpler case to deal with, at least for a case of constant kernel. But it turns out that it's incredibly unstable. If one makes tiny perturbations to the reaction rate, one gets wondrous behavior. And so there's kind of a whole field of mathematical physicists who've been looking at variations on constant kernel aggregation and some of its wondrous behaviors. So this may not be so much the realm of physics as applied mathematics, but just to give you a sense that there's a very rich range of behaviors that occur in this type of a system. So that is the end of my story of irreversible aggregation kinetics for now. And what I want to turn to in the remaining time of this lecture is to discuss aggregation kinetics in the presence of a steady input of monomers. And the reason why I want to study this particular case is that in many industrial processes, you're making, I don't know, I don't have an example off the top of my head, but the point is that in many chemical processes, one is feeding in input, there's some chemical reaction, and then you're trying to take out the output of this chemical reaction. And so the situation that's not as simplest to discuss then is aggregation kinetics with a steady input. And to make life as simple as possible, I'll talk about the case of steady input of monomers. And here you'll see there's beautiful mathematics and beautiful physical results that emerge. So I'm erasing now. So if you have questions, ask away while I'm erasing. Okay. Okay, so now we're talking about the case of Kij equals 2 plus steady monomer input. And you'll see that after we spend some time discussing the problem and solving it, I also want to show you a very beautiful analogy with homogeneous turbulence. And so it's kind of wide ranging, the kinds of things that I want to be discussing today. So in the case of steady input, so we're back now to the discrete equation. So I have Ck dot is equal to summation I plus j equals k, Ci Cj minus 2 Ck summation over all I equals 1 to infinity, sum Ci. And then I have steady input. So I need one more term here, which is plus a delta function, delta K1. So this is the Kronecker delta function, which is equal to 1 if K is equal to 1 and it's equal to 0 otherwise. So the equation for monomers only will have an additional 1 on it. The equations for everybody else will be just the same. And so we want to ask, what is the behavior, the time dependence of this equation? And so let's see what we can learn from it as simple as possible. So first point is that, as we saw in discussing irreversible aggregation kinetics, it was helpful, we learned something by looking at the equation for the total cluster density. So let's take this equation and sum over all K. And a natural question you might ask here is, well, does this steadily driven system go to a steady state or not? And how does it go to a steady state, or does it not go to a steady state? So let's look at this equation. So on the left-hand side, we have some CK. And so remember, that was what I called N. And so this is N dot. This is the total cluster density. And on the right-hand side, so when we do the summation over all K, this takes this restricted sum and makes it two unrestricted sums, Ci over sum over all I, Cj sum over all j. So this is nothing more than N squared. And then on the next term, we have, this is N again, and this is N again with a factor 2, so minus 2N squared plus 1. So we have N dot is equal to 1 minus N squared. And notice that if I set the left-hand side equal to 0, that means that there's no time of variation, that N, capital N, is equal to 1. And in fact, this is a very simple equation to solve, and the solution is N is equal to hyperbolic tanh of T. So we see that starting out with no clusters, if I start with an initially empty system, which is sort of the simplest initial condition I can choose, and it's natural here. If I start with an initially empty system at T equals 0, the N is 0, and then this will asymptotically go to 1 for large times. So this is the simple time dependence of the system. But what I want to focus on now is, so now we see that, like, for T going to infinity, we get a steady state. So let's look in more detail at the cluster mass distribution in the steady state. So let's look at the steady state mass distribution. So in the steady state, we're going to have 0 is equal to summation I plus j equals k, ci cj minus 2 ck sum ci plus delta k1. So that's the equation we want to solve. And once again, you are welcome to try and solve these equations one by one, starting at the equation for C1 and just see what comes out of it. But as we've learned, a much more effective and beautiful way to solve equations of this type that has this convolution structure here is to write the generating function. And so let's introduce, introduce g of zt, which will be equal to summation from k equals 1 to infinity, ck zk. Let's use the generating function. So let's take our original equation here, multiply through by z to the power k, that's a z or z, and sum from k equals 1 to infinity. And let's see what comes out of this. And since we've already done this exercise for the case of irreversible aggregation, that should be more, it should be familiar what's going to happen now. So when we do that, what we're going to get, so on the left-hand side is 0. On the right-hand side, so this is going to be zk, so I can write k because k is equal to I plus j. This is zi zj. So ci zi is one generating function. Cj zj is another generating function. So we're going to get g of z squared for the first term. For the second term, we have 2 ck zk, so that's twice the generating function. And this sum ci is like the generating function at z equals 1. So we're going to get minus 2 g of z, g of 1. And finally, we have the last term. We sum over all k, but the only term which is non-zero is k equals 1, which has a factor z, so plus z. So it looks like a very simple quadratic equation for the generating function. There's only one thing missing, which is, well, now this equation for g of z involves g at z equals 1. And to figure this out, let's just set, for z equals 1, see what happens. So we're going to get 0 is equal to g of 1 squared minus 2 g of 1 squared plus 1. So that tells me that g of 1 is equal to 1. So finally, I'm going to have g of z squared minus 2g of z plus z is equal to 0. So now we can solve for the generating function. It's just a simple algebraic equation. So I'm going to get g is equal to minus 2 plus or minus b, so that's 4 minus 4z, and the whole thing over 2. So I can write this as minus 1 plus or minus the square root of 1 minus z. So this is g of z. So two things to say about this very simple looking generating function. First of all, notice there's two signs here. Which one do we choose? Or do we need to choose both of them? And as we're going to see in just a moment, that the appropriate sign choice is, oh, by the way, I'm sorry, I can't. Solving a quadratic minus this term. So this is plus here. This is plus. So this is going to be 1 minus the square root of 1 minus z. We'll see in just a moment that we have to reject the other solution. So this is my solution. Second point is that we know now that the generating function encodes the full cluster mass distribution. If I can do a power series representation of this function, then the kth term in the series will give me the cluster mass distribution. So let's figure out the kth term in the series. And I'm going to be a little bit pedantic here because it's kind of simple, but kind of surprising. And you will see that there's a very simple closed form expression for the cluster mass distribution. So again, I'm going to erase. So in case you have questions, it's a good time to ask. So the goal is to now make a power series expansion of this function for general values, and find the general term in the power series. So let me do as a preliminary prelim. Let's look at 1 plus x to the power 1/2. And so from the binomial expansion of this thing, so let's just write out a bunch of terms. 1 plus 1/2 x plus 1/2 minus 1/2 x squared over 2 factorial plus. So I'm just taking this exponent and just subtracting 1 each time. 1/2 minus 1/2 minus 3/2 x cubed over 3 factorial. I'll do one more. 1/2 minus 1/2 minus 3/2 minus 5/2 x fourth over 4 factorial dot, 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 dot. And now what we're interested in is 1 minus z to the minus 1/2. And so let's write that out. So we're going to have 1 minus 1/2. And so x is minus z. So that's minus z plus 1/2 minus 1/2. And here I'll get z squared over 2 factorial. When I square a minus sign, that makes it a plus sign. And I'm going to have plus 1/2 minus 1/2 minus 3/2. And then here I'll have minus z cubed over 3 factorial. And then I have one more term, 1/2 minus 1/2 minus 3 halves minus 5 halves. And here I'll have z to the 4th over 4 factorial. So first point is that notice that sorry, God, there's a plus sign here. This is a plus sign. Sorry about that. Notice that all the terms, this is a negative term, this is a negative term, this is negative, all of them are negative. And then there's a leading 1. So when I take minus and a 1 here, all the terms will be positive. And that's why the sign choice here had to be the negative sign. So that's point number 1. Second point is, okay, so now we want to deal with like, what is the behavior of like the arbitrary term in this series? And the thing is that what I'm going to use is the gamma function. And so let me just remind you what the gamma function is. So this is a bit of an aside. So the gamma function is defined by k factorial. For integer values of k, it's equal to gamma of k plus 1. And so, you know, we know what k factorial is. It's product 1, 2, 3, dot, 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 all the way up to k. And Euler was the first one to define this, the Euler gamma function in this way. And part of the reason for doing it this way is that for integer values, well, for any value of k, you can write this as, whoops. Oh, here. You can write this as gamma of k plus 1 is equal to k gamma of k. So this recursion formula is how the gamma function is defined. And then you can see that for integer values of k, you go all the way down to gamma equals 1, gamma of 1, and that terminates the product. But it turns out, and this is the brilliance of Euler, is that you can define this recursion formula for non-integer values of k. And so what we're going to do now is use the gamma function for non-integer values of k to extract the asymptotic behavior of this series. So, you know, let's think about, for example, the product. So all I want to say is that, you know, this recursion formula for integer values of k stops at the end. But if it's a non-integer value, can you apply this recursion formula and it goes on and on forever? So in particular, for example, if I look at gamma of k plus a, so this is equal to k plus a minus 1.
Sorry for the interruption.
Sure.
Going back to the preliminary, in the equation that we previously wrote, we had that g was 1 plus or minus the square root of 1 minus z.
Right.
So why did we take in the preliminary 1 plus z to the minus half? Shouldn't be 1 minus z to the half and then expand that to justify using the minus rather than the plus?
So these were the two choices. Right?
Yes, exactly.
Okay. And so what I want to just say is that if g is equal to 1 plus the square root of 1 minus z, the power series would have all negative terms. Whereas if I choose 1 minus the square root of 1 minus z, this is all positive terms. And since, you know, we're dealing with a physical process where the number of clusters can only be a positive number, this solution we just have to throw away because it's not physical. Does that answer your question?
Yeah, I think in the second line in the preliminaries, you have an expansion of 1 plus x and just below it the 1 plus z, and Michael's wondering.
I'm sorry. I'm sorry.
It's a minus and then minus
Yes.
z is
Yeah. Sorry.
Yeah.
I'm sorry. This
So
should be
z is
minus
x.
Yes. Yeah. Okay. Thank you. Okay. Very good. Okay. Anyways, so by this recursion formula, the gamma function k plus a it just goes k plus a minus 2, k plus a minus 3. It goes on, and it goes on forever. So if you want, and you see here what we have is something that's kind of like this, because here, like a is like a half integer, because this is like a half integer number. So if we, and this thing stops. So if we want something like this, but having it stop, the only way we can make it stop is that we can divide it, for example, by gamma of a. And so this will also be an infinite product that starts at a minus 1. So downstairs we'll have a minus 1, a minus 2, all the way down the road. Here, there's a term that will eventually reach a. And then there'll be a minus 1, a minus 2, dot, 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 dot. So by dividing by this, all of these infinite terms will cancel out. And so we'll have that the ratio of gamma functions is equal to this finite product. And so that's the trick I'm going to use now to re-express everything here in terms of the gamma functions. So let me write this as 1. So there's a 1/2 out in front everywhere. So let me keep that 1/2 separate. And then I have, and let me write it this way. So it's 1 minus 1/2, because everywhere it's negative terms. And then I have this k factorial for each term, but k factorial is 1. Oops, so actually, let me just skip to the kind of final result. So I'm going to infer from this that ck is equal to minus, because of the minus sign from everywhere. There's the 1/2, which is everywhere. And then I have 1 over k factorial, which is gamma of k plus 1. And now upstairs, what do I have? Well, so for the kth term, if k is equal to 4, 5 is 4 minus 3/2. And here, 3, this 3/2 is 3 minus 3/2. So the top term here is going to be gamma of k minus 1/2. And so when I start doing this expand like this, using this formula here, the very first term will be is going to be product of k minus 3/2, which is exactly this guy. And then this gamma function just has an infinite product, but we want it to stop at 1/2. And the way to make it stop at 1/2 is put downstairs gamma of 1/2. So that's the answer. And this is in some sense like the elegant way of taking this power series and trying to extract the high order terms in this power series. So the point here is that whenever you're dealing with an expansion of a binomial with a non-integer coefficient, you'll end up with these sorts of products, which are gamma function like for non-integer values of the argument. And one can just proceed in the same way as one did for the good old binomial expansion. So this is the main result here, is that we've now found the exact form. Whoops, sorry. There's one more piece to get the exact form for ck, because remember that the generating function, g, was equal to 1 minus the square root of 1 minus c. So what we need to do is take 1 minus this thing. And so the 1 cancels the 1 over here. And the minus sign gets rid of the minus sign here. So this is a plus. So now we have the exact answer. So anyway, this is kind of elegant and kind of cool, but also perhaps a bit opaque, because you might say, well, how does this depend on k? And now what we can use is Stirling's approximation. And you may remember from somewhere, I hope you remember from somewhere, that k factorial, the Stirling approximation is equal to k to the k, e to the k, divided by the square root of 2 pi k. Stirling's approximation. And maybe this is more familiar in the form of this way. Log of k factorial is equal to k log k plus a square root of 2 plus 1/2 log of 2 pi k. Maybe that may look a little bit more familiar to you. So anyways, what we can do then is apply Stirling's approximation to here. And at this stage, I'm going to invite you to do it because it's very straightforward and everything follows very directly. And there's one more feature, which is that what is the value of gamma 1/2? And it turns out that this is equal to the square root of pi. So asymptotically, this scales as, so we have 1/2 root pi in the denominator. So this is overall factor 1 over the square root of 4 pi. And then we have this guy and the difference in the exponents. So now let me mention one more thing, which is that using Stirling's approximation for this ratio, one finds that, and so let me just write something that comes from like mathematical tables, which is gamma of k plus a divided by gamma of k plus b, limit. Let me make my penmanship a little better. So limit k going to infinity. This thing is asymptotic to k to the a minus b. And so this comes by applying Stirling. So again, what I invite you to do is apply Stirling's approximation to this product using gamma function in terms of the factorial. And you will find with not very much labor, this fact. And so here, the difference in the exponents is there's a -1/2 here and a 1 here. So this will scale as k to the -3/2. So this is the main result here, is that in the steady state, the cluster mass distribution has a power law tail, k to the -3/2. And so let's plot this to get some feeling for what's going on here. I guess I don't need all of this. This is all I need to save. So the cluster mass distribution. So let's plot log ck as a function of k. And so this is a power law with an exponent -3/2. So on a double logarithmic plot, this will be a straight line of slope -3/2. This is not quite the whole story because what I've solved for is the steady state. And clearly, if I turn on my reactor at some time, the clusters are getting larger and larger and I'm building up and there's a steady state part of the distribution, but there's also a tail over here because clusters haven't had a chance to grow as large as the maximum size. So let's call Kc the maximum size of clusters that can actually develop. And now using physical reasoning, we can figure out what this Kc is and we can actually get time-dependent information from the time-independent solution. So notice, so what is Kc? This maximum cluster size. Well, we must have that if I look at the total mass in the system, Kck dk, integrated from 1 up to the maximum cluster size that can exist in the system. So by construction, I turn on my definition, I turn on my reactor at 7 in the morning, and after a time t it's been running, the total mass that I have in the system has to be equal to t. There's no other way. And that has to equal the total mass under this whole cluster mass distribution. And so here's the total mass. And now what we can use is the steady state form, because in this region, the main part of the distribution, we already have reached the steady state. We haven't quite reached it here yet, but it's going to play an infinitesimal role in the answer. And so this scales as the integral of 1 to Kc, k, and Ck scales as k to the -3/2 dk. And so this is k to the -1/2 dk, which scales as Kc to the power 1/2. And this is equal to t. So we find our main next result, which is Kc scales as t squared. So the right-hand tail of this distribution is moving to the right at a rate t squared and leaving behind a nice, smooth, steady state distribution. So this
A question, is there a lower cutoff for the distribution, like CK min or K min?
well, the lower cutoff is 1. It's just basically, it's like, what is the minimum size that you're inputting into the system? So for the case of monomer input, then our minimum size is 1, which in logarithmic units is 0. So log of 1 is over here, and that's your minimum size. But yes, if you're feeding in like clusters of mass 10, for example, only 10, then there'd be nothing below 10. So any questions with this?
Why is the integral equal to t?
Well, because this integral here, this is by definition, this is the total mass. You know, everything under here is a total mass. Everything under this curve. And so we want that the total mass has to equal the amount of mass that I put into the system. And if I'm inputting monomers at rate 1, that means after time t, the total mass in the system is also equal to t.
Okay, that's clear.
Okay, great. Okay, so this is, I think, a reasonable stopping point. So let me take a 5-minute break. And if you want to ask questions, great. Otherwise, I'm just going to erase the board and not say anything. And I'll see you in 5 minutes from now.
A question, just to follow up on the minimal size. The fact that the distribution has monomers means that you have a lower cutoff. And we know if processes have lower cutoff, are they doomed somehow to be governed by powered laws?
No, not, I mean, you know, I could imagine that there's also fragmentation going on as well as aggregation, in which case, if I'm feeding in, say, monomers at a fixed rate, and they are aggregating and fragmenting, then that means that there'll be no lower limit to the cluster mass distribution. I have to admit, I don't know the answer for what is the distribution in that case, but that might be a fun thing to work out and understand, like, what is the role of the lower cutoff? I know that people have looked at fragmentation, pure fragmentation kinetics, where you just take a cluster of a given size and you smash it with a hammer over and over again ad infinitum to make finer and finer dust. And you can also, for that system, imagine that if you start with, say, a cluster of mass 1, that's an upper cutoff, and then there'll be no lower cutoff. And that might have, I know that that's been solved, and I don't know the answer off the top of my head, but that has a problem where there's an upper cutoff and no lower cutoff. But if you have aggregation and fragmentation plus input, now that will give you a distribution with no upper cutoff or no lower cutoff. And I imagine it's been solved before, but I don't know what the answer is.
Yeah, I know the answer, but without the steady state, the fragmentation and coalition, diffusion and fission and fusion somehow. And the power law is something like 5/2. So there is a steady, but without steady input of monomers. So,
right.
Yeah. But
I
I don't know.
But the thing is that if there's no input of monomers, then the system actually is always, okay, so I mean, in some sense, the system can go to an equilibrium because there's a competition between aggregation and fragmentation.
Right.
Yeah. Okay.
Okay.
Okay, so what I'm going to do now is, it's a bit of a digression, but this problem of steady monomer input with aggregation has a beautiful analogy with homogeneous turbulence. And so I feel that this is the analogy is so close and the results are so powerful that I just want to spend a few minutes talking about homogeneous isotropic turbulence. So let's imagine we have a fluid, and instead of having steady monomer input, we're going to have steady energy input, and Navier-Stokes equation. And in some sense, this is something for any of you who have ever paddled a canoe or paddled a kayak or rowed a boat, you may have seen this, which is that when you take your paddle and put it in the water and pull, you will create eddies. And these eddies, if you watch them carefully, will break up into smaller eddies and break up into smaller eddies ad infinitum. And if you've never done this experiment, I urge you to do this experiment at home. It's a very simple experiment and it's really fun. Is that you take a cup of water in a glass, you take an eyedropper and put in either food coloring or an ink, and just take one drop and drop it and watch what happens. Has anyone done this experiment? Nobody's done it. So I urge you to do it because it is just so incredibly beautiful to see physics in action, because what happens is there will be a vortex ring when the drop hits the fluid, a vortex ring is created. This vortex ring will develop all kinds of undulations, which will then break up into smaller vortex rings, which will break up into smaller vortex rings. And this feature of energy input at one scale going into excitations at smaller scales or larger wave numbers is the basic feature of homogeneous turbulence. So when you feed in energy at one scale, it breaks up and goes into smaller scales. And there's a very famous quote by a guy named Lewis Fry Richardson in the 1920s, who was one of the early pioneers of studying turbulence. And so he had this incredible quote, and let's see if I can remember it. It's like, big worlds have lesser worlds that feed on their velocity, and smaller worlds have even smaller worlds, and so on to viscosity. So it's just this feature that, energy input at a large scale gets fed in, because of the nonlinearity of the Navier-Stokes equation, just as aggregation is a nonlinear differential equation. So it mixes different masses. Here you mix different wave numbers together. And so energy input at one scale or one wave number gets fed in and broken up into smaller scales or larger wave numbers. And so what was found in the case of when you're feeding in energy in a homogeneous fashion, like with no spatial structure at large scales, if one looks at the energy spectrum, so now I'm looking at the same thing here as a function of logarithm of k, where here k is the wave number, which is equal to 1 over the wavelength. And here I'm plotting logarithm of the energy density at wave number k. One found a power law behavior in the steady state. And then the question was, what is this exponent? And so in the 1930s, Andrei Kolmogorov actually came up with a very simple mean field argument to find this exponent, and it was made him very famous, and it's called the Kolmogorov 5/3 law for the scaling of homogeneous isotropic turbulence. And what I want to show you is that by dimensional analysis, we can obtain the same exponent with just good old dimensional analysis. And so I want to try and impress upon you, first of all, the power of dimensional analysis, and also the analogy between the mass distribution in aggregation and the energy spectrum in turbulence. So let's do that. So I don't need this. So first point is that there's input, so there's energy input over here. Just as over here, there was mass input. So there's going to be a very close analogy. So let me call it, so I don't mix up, let me call this epsilon of epsilon. This will be defined as the energy input per unit time. So I'm imagining I'm stirring my reactor, and so I'm putting in a certain amount of energy per unit time. And clearly, if my system, to make like the system size independent, nothing should depend on the size of the system because this is homogeneous isotropic turbulence. If my system is twice as big, I'm going to have to feed in energy twice as fast or twice as much to have the same degree of excitation in the system. So what I should write here is energy input per unit time per unit mass. This is in a properly normalized energy input per unit time. And so let's ask ourselves, what is the dimensions of this quantity? This has units. Well, energy is mass. So move this out of the way. So this is log K. So in units, we have mass over length squared time squared. But downstairs, we're doing it per unit mass. So that gets rid of the mass per unit time. So that's time. So this is equal to units of L squared over T cubed. Second point is, now let's look at our, energy density. So if we're looking at a particular wave number, we're asking how much energy is in this wave number range. So here, let me call E of K. This is going to be the energy density per wave number. And so let's look at the units of E of K. So this, again, energy density per wave number. Well, so energy density, so that's again length squared over T squared. And density means divided by mass, so the mass has gone away. And divided by wave number, so wave number has units of 1 over length. And so this is times 1 over L. So this has units of L3 over T squared. And the point here is that we want, E of K, it's some function which we don't know of the energy input. But the thing is that now that we know the dimensions, we have a lot of information available to us, because it's got to be that that the energy density has to have the same time units as before. So it must be that this thing has to scale as energy input, energy density input to the power 2/3. Because you see, if I have energy to the 2/3, I'm going to get, this is of units of L to the 4/3 divided by T squared. So we have the right time dependence by having that the energy density in any given wave number is proportional to the energy input density to the power 2/3. But there's a problem here, because the units of this is all messed up. The units of energy density have to be length cubed. So we must have another length to the power 5/3. So let me put here L to the 5/3 to denote that there's some other length in the problem that we have to find that gives us the right units for the energy density. And so what is this other length? Well, there's nothing in the system. There's no boundaries, there's no length, there's nothing. The only thing which has units of length is the wave number, the inverse wave number. So I guess, so what I want to say then is that wave number, which is 1 over a length, is the only other variable left in the problem. So it has to be that this length should be 1 over the wave number. So this means we're going to get so that means that this thing should be proportional to K to the minus 5/3. So this is called the Kolmogorov law for the scaling law of homogeneous turbulence. And so this is an incredibly deep result in fluid dynamics. And you see that it has a very simple way of deriving it by dimensional analysis. So I wanted to show this just because it's so cool and so broad ranging and so simple. And you see that there was kind of a one-to-one correspondence between aggregation with input and fluid dynamics with energy input at one scale that then cascades to smaller scales. So that's the story with Kolmogorov. So any questions with any of this? Okay. Well, so now, so this sort of ends like the first, in some sense, this is the end of like the second part of the course. I first talked about random walks and the birth-death process. Now I've been talking about aggregation kinetics. And so for the next two lectures and like for the last few minutes of this lecture, I'm going to be talking about complex networks. And so for the rest of today, I'm really not going to do any derivation. I'm just going to do some speaking, and I might end a few minutes early here because I should have had, I'll just end a few minutes early here. So as I say, the next two lectures will be on complex networks. And I'm going to talk about several families of complex networks. And so maybe I will write a few things on the blackboard. And first of all, like, why do we even bother studying complex networks in the first place? And as you'll see that the tools that I've tried to introduce over these 4 lectures, we will be using them over and over again and understanding the dynamics and the structure of various types of complex networks. So I hope that with the tools that you've learned in the past 4 lectures, some of what I'm going to present in the next 2 will seem very familiar to you and very comforting. So that's one point, is that this is a very paradigmatic problem in non-equilibrium statistical physics because it's a many-body system. It's a system with many nodes and many links that is evolving in time. And it's very well suited for studying using the tools of non-equilibrium stat mech. But another feature about this is that complex networks were kind of, it's been studied on and off for like almost 100 years. But somehow in the late part of the last millennium, the availability of large-scale data allowed us to actually see that much of nature is described by complex networks. And this fueled an incredible explosion of interest and effort, starting basically in the year 2000, and it's continuing to this day. So, it's sort of this marriage of, applications suddenly becoming relevant because one could actually see the data, and a beautiful application of non-equilibrium statistical physics that has given rise to this very vibrant field of understanding the structure of complex networks. Mathematicians have been studying graph theory for like more than 50 years. And so there's also been a very productive marriage between mathematical techniques and physical techniques here. And so the kinds of complex networks that I'm going to be presenting to you is, first of all, the very first example is the so-called Erdős Renyi, I guess there's an accent there, random graph. And this is in some sense the most simple-minded and most mean field-like of all the complex network models. And in the Erdős Renyi random graph, one imagines you have like a system of nodes, and you have a certain number of links that you just randomly sprinkle joining the nodes as you want. And so there's no geometrical structure to this network. There's just nodes and links. And as we're going to see, as you increase the density of links, there is a phase transition. When the number of links is small, you'll get isolated nodes and maybe small clusters of nodes, but you'll have many small clusters. And as you increase the link density, one finds a phase transition, a percolation transition between a phase where basically everything is connected into one huge cluster when the concentration of links is high enough. And as you decrease the concentration of links, it'll break up into lots of small clusters. So the crucial feature about the Erdős Renyi random graph is the percolation transition. And as you're going to see, this percolation transition is related to what is called product kernel aggregation. So product kernel aggregation is where the reaction rate Kij is equal to I times J. So as I mentioned, I think, at the beginning of the last lecture, there's a very few exactly soluble models in aggregation kinetics. And product kernel aggregation is one of them. And so if I had another two lectures, I would show you how to solve product kernel aggregation using the generating function technique. It's the same idea, the same approach as what one did in the case of constant kernel, but it's actually much more advanced, and it's not suitable without much more time. But as I'm going to write down the solution for product kernel aggregation, and from that we'll infer about important facts about the percolation transition in the Erdős-Renyi random graph. So that's one topic. The next topic that I'm going to present is what might be called sequentially growing networks. And so what I have in mind here is the notion that I have a network of a given size, and I'm building it up by just adding nodes and links in a sequential fashion. So the simplest version of this is, let's imagine that we have some network. So it's a collection of nodes and links. Maybe there's something that looks like that. And then in comes another node. So here's a new node coming into the network, and it joins to a single node of the network. So that's what I mean by sequentially growing networks. You have a network of a given size, the new node comes in, and it attaches either to one node of the network or to multiple nodes of the network, making a still larger network. And one can ask, what is the structure of this type of a network? And it turns out that there's several flavors of these networks. There's random attachment, in which whoever I attach to, I don't pay any attention to anything about the properties of the node I'm attaching to. I just pick a node at random and attach to it. And then there's what's called preferential attachment. And preferential means that, in fact, what I pay attention to is the degree of the node. The degree is a number of links. Here is a node of degree 3. So and here's another one of degree 3, degree 2. So the degree is a number of links attached to a node, or maybe more, socially, we can think of it as the number of your friends. And so preferential degree-based attachment which means that if I have a lot of friends and a new node comes to the network, it's more likely to attach to me than to somebody who doesn't have very many friends. And so this is what's called preferential attachment. And as we're going to see, there's many different subcases here that are all interesting. There's sublinear preferential attachment, in which my rate of attaching is sublinear, it grows sublinearly in my degree. There's linear preferential attachment, which sometimes is known as the Barr-Bossi-Albert model. And that's a very famous paper. That's actually the most cited paper in all of science in the history of that journal. And then there's superlinear preferential attachment. And so we'll spend a fair amount of time solving these networks and understanding their degree distribution, which in some sense is the basic observable in this type of a system. And then I'll talk about two more variations in this. One is what might be called densifying networks. And what I mean by densifying network is something that presumably, many of you are on Facebook, and in the early days of Facebook, I don't think it happens anymore, but when I first joined Facebook, so I joined Facebook and I connected to a number of my friends, and every couple of days I get an email from Facebook saying, well, we see that your friend A has these friends A1, A2, A3. Why don't you connect to them? And I get all these messages, and I typically ignore them, but every once in a while, oh yeah, it's a good idea. Like, this person is a friend of my friend, and it seems like it'd be good to be friends with this other person. And so what this means is that if there's an existing network, it means that, here I am, and I have my friends over here. And then Facebook says, well, your friend has this person as a friend. Why not join to this person as well? And so this feature of adding new links without adding new nodes gives rise to a network which densifies. And as we're going to see, the structure of densifying networks is extremely rich. And finally, and I'll leave this as kind of a mystery at the end, I'm also going to talk about redirection. And what I mean by redirection is that suppose that I'm a new node and I'm going to attach, and here I'm a new node, and I'm going to try and decide who I'm going to attach to. And so I'm thinking, well, you know, this person looks interesting, that person looks interesting, that person looks really interesting because they've got a lot of friends. And so I'm about to say attach over here, you know, Joe is someone who looks interesting, but then I see that Joe has a lot of friends. Before I make the attachment, all of a sudden I say, well, let me go to the neighbor of Joe because this person's got lots of friends and this is a better person to attach to. So this notion of redirection turns out to be, first of all, a very simple algorithm. It turns out that it's a very powerful way of actually studying linear preferential attachment in a very elegant way. And it also has its own very strange properties that I'll hopefully get to next time. So to my mind, this is a good place to stop. Just to let you know, in the next 2 lectures, I'm mainly going to be working from slides because some of this is better to illustrate via slides. You see things evolving in time. So I will be mostly slide-based over the next 2 lectures. So that's it for today. And I'll see you, I guess, on Wednesday.
Okay,
Thank you.
thank you so much.
Okay.
Great.
And if there's any questions at the end here, I'm here.
Questions? No questions.
Okay,
Okay. Thank you so much.
sure.